Hello everybody. Today we're going to look at quadratic functions. Our main objectives here today is going to be to first define what quadratic functions are, look at some of the basic characteristics of quadratic functions from the graphical perspective, and then look at easy methods or simple methods for sketching graphs of quadratic functions. So let's begin by first of all defining what quadratic functions are. So, a quadratic function we define as any function that has one of the following basic forms. The general form, which is f of x equals a times x squared plus bx plus c, or the standard form, or what I like to call the vertex form, which will become clear in a little bit, which is a times the quantity x minus h squared plus k. Now, some examples of these different types of forms, just to give you an idea of what they look like. The first example for the general form might be examples like, for example, y equals 2x squared minus 5x plus 4. All right, so here, the main characteristics, you have an x squared term, you have an x term, you have a constant term. So that's one example of the general form. The standard form example might look something like this. Y equals negative 2/5 times the quantity x plus 1 squared plus 4. So this is an example. So now notice with the standard form, you generally have a squared expression, and then on the outside you have it multiplied by a constant, perhaps, and then a term added at the end. Now, both of these are considered quadratic functions. Now, the main thing that makes a quadratic function is that it's a polynomial function that has a degree of 2, which is to say that it's going to be an expression that contains an x squared term in it. Now, when we look at graphing these types of functions, okay, well, the most basic type of function or quadratic function is the squaring function. So now when we take a look at the squaring function y equals x squared, now this type of function you should already be familiar with. Basic squaring function, if we look at some of the points here, we know that 0, 0 is a point, 1, 1, 2, 4, 3, 9, then negative 1, 1, negative 2, 4, negative 3, positive 9. So if we connect the dots here, okay, we end up with a graph that looks something like this. Now, from previous material, you may have already learned about the squaring function. It was one of the basic library of functions that you should already be familiar with. Now, this is sort of the simplest type of quadratic function that you can have. Now, there are other types of, if we look at the graphs of other types of quadratic functions, we'll begin to notice something rather interesting, that all the graphs of quadratic functions are going to have the same type of shape. So if we look, for example, here with these two examples here, y equals x squared minus 4, well, now this equation, the graph of this, is going to look just like x squared. The main difference here is that it's going to be shifted down 4 units. All right, so y equals x squared minus 4 is the graph that we have in black. The other function, y equals 2x squared plus 6x, if we look at the graph of this function, we'll see that this graph looks something like this. All right, so if you notice the x squared graph and the two examples that we have here, y equals x squared minus 4, and y equals 2x squared plus 6x, all of these graphs have the same type of shape. Right? They may be oriented differently in that they're in different locations, or one, as we can see, was actually pointing downward as opposed to pointing upward. But the general shape, the curve, is identical, and that's going to be standard for all quadratic functions. And in fact, because all the shapes look the same, we have a specific name for the graphs of all quadratic functions. We refer to these as parabolas. All right, so the graph of a quadratic function is what we call a parabola. Now, as a quadratic function, parabolas are going to have one of two basic orientations. Either the graph will be pointing upward, or the graph is pointing downward. Now, the orientation of a parabola, we also refer to that as its concavity. So when a graph is pointing upward, you say that the graph is concave up, and when it's pointing downward, we say that it's concave down. Pretty simple to remember. Now, some of the other characteristics of these types of functions, or the graphs of these functions, is that regardless of the orientation, you'll notice that there's always going to be a turning point of the graph. In the case where it's concave up, there's a bottom point or a minimum value where it transitions from decreasing to increasing. And then in the case of it being concave down, you see the opposite happening, going from increasing then to decreasing. Now that point where that occurs has a special name. We refer to that point as the vertex of the parabola. Now, one other thing to note here is that when we take a line, a vertical line, and pass it through the vertex of the parabola, this line actually splits the parabola in half. So it actually becomes a line of symmetry for the parabola. And so, of course, this particular line is actually known as the axis of symmetry. Excuse me. Okay, bit of a sneeze there. All right, so now when it comes to sketching or graphing a parabola, we can plot points. Just choose values of x, plug them into the function, and get corresponding y values. But now, is there an easier way that we can sketch parabolas or graph parabolas? And in fact, there is. And much of it comes down to these basic characteristics of the graphs of quadratic functions, of parabolas. If you recall from linear functions, remember a linear function has a graph that's a straight line. And as long as you know the slope of the line and the y-intercept, you're able to graph the line. You can do it very easily. So now when it comes to parabolas, we can draw a pretty good sketch, a decent sketch of a parabola if we know the vertex of the parabola and the concavity. Because having the vertex basically gives us the turning point. The concavity tells us whether it's going to point upward or downward. Now, if we wanted to draw a more accurate graph, we will need to know to what extent the graph or the parabola is going to be distorted. That is to say, how much of a vertical stretch or compression that we're going to have. And so for that, we will need some additional points in order to figure that out. So now let's take a look at how we can find those basic characteristics, or how do we go about sketching a graph of a parabola. All right, so the process is pretty straightforward. The first basic step to graphing a quadratic function is going to be to find the vertex, the turning point. Now, how do we find the vertex? Well, that depends on how the quadratic function is expressed, which form it's written in. If the quadratic function is written in standard form, or the vertex form that we talked about, a times x minus h squared plus k, the vertex is simply going to have the coordinates h, k. So you can see why I refer to this as the vertex form, because the form or the vertex is actually right there in the equation. So you don't really have to do a whole lot to figure out what the vertex is. Now, if the function is, or the quadratic function is in general form, ax squared plus bx plus c, then to find the coordinates of the vertex, the x coordinate of the vertex will be given by negative b over 2a. So a, b, and c are just the coefficients of the terms of the um, quadratic expression. So h is negative b over 2a. K will be f of negative b over 2a. So in other words, once you find out what the x coordinate is, you can determine the y coordinate of the vertex by simply plugging it into the function and then determining that value. Now, we're going to do a couple of examples later on to show how these steps play out. All right, and we'll see how that works. The second thing is you want to determine the concavity, whether it's going to be concave up or concave down. And so here, you just look at the value of a, and it doesn't matter what form the quadratic function is written in, whether it's in standard form or general form, the a value is going to be the same. So if the a value is a positive number, then the concavity, it will be concave up. If it is a negative value, then the parabola will be concave down. So now once we have the concavity, you have the vertex of the concavity will give you the general structure of the parabola. Now, to get a more accurate looking graph, we will need some additional points, and the best points to plot in this case are going to be the x and the y intercepts. So to find the intercepts, the y-intercept, if you recall, is the point where the graph will cross the y-axis. So to find that point, you're going to set x equal to 0 and solve. And then to find the x-intercept or the x-intercepts, you set y or the entire function equal to 0 and solve. Now, in the case of the x-intercepts, to find that solution, you are going to be solving a quadratic equation. So I'm assuming at this point that you do know how to solve quadratic equations by various means, like factoring, the square root method, or when all else fails, the quadratic formula. And so when we do the examples, you'll see how this plays out as well. Now, once you have the vertex, the concavity, and you know the intercepts, that's going to be more than enough information for you to sketch a good graph of the function. And so then you just simply plot the points, the vertex, the intercepts, and then sketch the graph. Now, one thing that's also good about this method is that all of these particular things that we find should match up with each other. That is to say, if you know a graph is concave up, but yet you find the intercepts and the intercepts are indicating that it's going to be concave down, that's going to let you know that there's a mistake that was made somewhere. Either you misinterpreted what the concavity is going to be, or perhaps you need to recalculate your intercepts. So every single part, the vertex, concavity, the intercepts, all of those will be in agreement with each other when you work out the problems. So now let's go ahead and take a look at a couple of examples. And I'll put this on the next screen here. So we'll start with the first example. Here we have f of x equals -2 times x minus 3 squared plus 2. So the very first thing here is that we want to determine the form that the equation is written in. As we can see here, the graph or the function is written in standard or vertex form. And so that's good news because that'll make things easy for us to determine what the vertex is going to be. All right, so the first thing we want to do, find the vertex. Okay, I'm going to change my color here. All right, so the vertex of the parabola, now as I mentioned before, it's going to be located right there in the equation itself. Remember the standard form, it's a times x minus h squared plus k. So here h is going to be equal to 3. So the x coordinate of the vertex is going to be 3. The y coordinate of the vertex is going to be 2, the k value. Okay, so it's right there. The one thing to note here is that the value of h, the x coordinate of the vertex, will be opposite in sign of the number that we see in the x minus h squared. And that's why they have x minus h. So our h value will be opposite in sign of what we see. So being x minus 3 in this case, the x coordinate was a positive 3. If that were x plus 4, for example, then the x coordinate of the vertex would be a negative 4. All right, so now the vertex being 3, 2, now we also want to determine next what the concavity is going to be. So now in this instance, the a value is negative 2. So with the a value of negative 2, that being less than 0, that tells us that this is going to be concave down, because being negative 2, that's less than 0, and therefore it's going to be concave down. Now at this point, we could actually go to the graph and plot what we have here. Just considering what we have to look at or to work with, the vertex being 3, 2. So if we go to the point 3, 2, which is located about here, and with it being concave down, we know at this point it's going to be working downward from this vertex. So now that also tells us that the vertex, because it's concave down, will be a maximum point. All right, so we know that from this point, it's going to point downward. Now we don't know how it's going to point down because it could go down. It could be sort of have a wide berth, or it could be going down very quickly. That we don't know, but that information we can find out by plotting additional points, namely the intercepts. So let's go ahead and do that. All right, so now to find the x-intercept, or we'll start with the y-intercept first, because that'll actually be a little bit easier for us to find. All right, so for the y-intercept, we set x equal to 0. So now if we do that here, we're basically evaluating the function at 0. So we're finding f of 0. So f of 0, we plug in 0 for x. So that'll be negative 2 times 0 minus 3 squared plus 2. All right, and so if we calculate that, we'll have negative 2 times negative 3 squared plus 2. So negative 3 squared is 9. So this will be negative 18 plus 2, which is equal to negative 16. So our y-intercept will have coordinates 0, negative 16. All right, now that's going to take us a little bit outside the graph that we have here, but at least we know that from that perspective, since we know the point's going to be down on the bottom here, it is pointing downward and concave down, so that basically is going to be in agreement with what we determined before. All right, so now let's find the x-intercepts. So for this, we set y equal to 0, or we're just setting the function equal to 0, and we're going to solve it. So we have negative 2 times x minus 3 squared plus 2 equals 0. So now to solve this, we want to isolate the squared part. We can use the square root method here. So we subtract 2 from both sides of the equation. This will give us negative 2 times x minus 3 squared equals negative 2. Our next step will be to divide both sides by negative 2 so that we can isolate the squared part. So that gives us x minus 3 squared equals positive 1. We then apply the square root property, or just take the square root of both sides. So we do that, we'll have x minus 3 equals plus or minus square root of 1. Because remember, when we take the square root of both sides of an equation, you have both the positive and the negative square root. So square root of 1 is 1. So you have x minus 3 equals plus or minus 1. And so then finally adding 3 to both sides, we'll have x equals 3 plus or minus 1. So that's two values, x equals 3 plus 1, or x equals 3 minus 1. So 3 plus 1 is equal to 4. 3 minus 1 is equal to 2. So therefore, our x-intercepts, we have two of them. The x-intercepts here would be the points 4, 0, and 2, 0. And so now we plot those points as well. So we have the vertex. The y-intercept was a little bit outside the range of our graph, 0, 16. And the x-intercepts were 4, 0, and 2, 0. All right, and so now just with that information, we can now sketch a pretty good parabola. All right, and so there you have the graph of that particular parabola, negative 2 times x minus 3 squared plus 2. Now notice here that all of the information that we found, down to the y-intercepts, the x-intercepts, they agreed with what we determined beforehand about the concavity being down, and also it helped to support the value that we got for the vertex. So as I said before, all of these values should pretty much match up very well. They should agree with each other. All right, so now let's take a look at the second example. I'm going to clear this off. And so our second example will be the second function here, g of x equals x squared plus 8x minus 5. Now, this one's going to require a little bit of work here because now this equation is in general form. Okay, and I'm going to go ahead and sort of scratch this first one out so we don't get confused, because it looks like we're going to need the whole board to finish this. So the first thing you want to do is find the vertex. Now, because this particular equation is in the general form, the way that we find the vertex, that's going to require a little bit of work for us. All right, so first of all, to find h, that's going to be equal to negative b over 2a. So in this case, what's a, b, and c? Well, a is equal to the coefficient of x squared. So in this case, that's going to be 1. B is the coefficient of x, which is 8. And then c is the constant term, which is negative 5. So in this case, negative b divided by 2a, that's going to be negative 8 divided by 2 times 1. So it'll be negative 8 divided by 2, which is equal to negative 4. So that's the x-coordinate of the vertex. For the y-coordinate of the vertex, that is to say k, that's just going to be f of negative b over 2a. Now, since we already found that value to be negative 4, that means we're just finding f of negative 4. So to find that value, what do? We take negative 4 and we'll place the x with 4 in this function. Now, I made a mistake here. The function, we named this g of x, so this should be g of negative b over 2x and g of negative 4, but you get the idea. We're still going to be doing the same thing. So we plug in negative 4 for x, so that'll be negative 4 squared plus 8 times negative 4 minus 5. So negative 4 squared, that's 16, plus 8 times negative 4 is negative 32 minus 5. And so this is going to give us negative 16 minus 5, which is equal to negative 21. All right, so our vertex here will have coordinates negative 4 and negative 21. All right, so now in this one, the y-coordinate, negative 21, is going to be really far outside of our range. So I think that what I'm going to do in this case is that I'm going to have to scale the values here. And so we'll do that at a later time. But let's find the rest of the numbers, the rest of the information from here. All right, so we have the vertex. So now we need to determine the concavity. All right, so now is this going to be concave up or concave down? Well, in this case, the a value is equal to 1. And that's a positive number. So therefore, this graph is going to be concave up. So from the vertex, okay, wherever it is, okay, we know the graph is going to be moving upward. Now, just with that knowledge, with that in mind, we can already surmise that the graph is going to have a couple of x-intercepts, and that those x-intercepts, it's going to have a couple of x-intercepts, and so we should be able to see the graph moving upward from the vertex, which is going to be in the third quadrant. All right, so now let's find out what the intercepts are going to be. So we'll start with the y-intercept. All right, so remember that the y-intercept, we set x equals 0. And then for the x-intercept, we set the function, or y, equal to 0. So in the case of the y-intercept, when we set x equal to 0 here, okay, we're just going to be replacing the x with 0. So y, that's going to be 0 squared plus 8 times 0 minus 5, which is going to be equal to negative 5. So our y-intercept will have the coordinates 0, negative 5. For the x-intercepts, now here's where we have to set the whole function equal to 0. Now this is going to require a little bit of work here, because if we take the function x squared plus 8x minus 5, and we set that equal to 0, note that this function is not factorable. So since we can't factor it, we're going to have to use the quadratic formula. So recall the quadratic formula. That's equal to negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. So now if we apply the formula in this problem, we have x equals negative 8 plus or minus the square root of 8 squared minus 4 times 1 times negative 5, all divided by 2 times 1. So now if we simplify this, we have negative 8 plus or minus the square root of 8 squared, that's going to be 64, plus 20, so that's going to be the square root of 84 over 2. Now we can simplify the radical here, right? That is negative 8 plus or minus 2 times the square root of 21 divided by 2, which would further reduce down to negative 4 plus or minus the square root of 21. Now, the important thing here is that since our goal is to sketch a graph of the function, we don't have to get so caught up in trying to simplify our results too much, because we're going to have to get some approximations here in order to plot the points on the graph. So now if we look at the two solutions here, for negative 4 plus the square root of 21, if we calculate that, negative 4 plus the square root of 21, that gives us a value of approximately 0.6. I'm just going to round it to the nearest 10. And then for negative 4 minus the square root of 21, if we evaluate that, that is approximately equal to negative 8.6. So our x-intercepts here approximately will be 0.60 and then negative 8.60. So if we plot their approximate locations, 0.60 will be a little bit between 0 and 1 on the x-axis, a little closer to 1, and then negative 8.5 or negative 8.6, I should say, 0, will be between negative 8 and negative 9. All right, so now bringing this together with our approximate, well, with our vertex. Now the vertex, remember, was way down here, so it was like negative 4 and negative 21. All right, I'm not going to be doing this really much justice here, but we can get an idea once you have that value. From there, we're just basically drawing the parabola. Okay, and so our drawing isn't the best in the world, particularly right here. Okay. Okay, so if you can just imagine the vertex here is at the point -4, -21, we see here that we do indeed have the graph of the parabola. All right, now this one did require a little bit of work for two reasons. One, the equation was written in general form, so that required a little work for us to find the vertex. And the second thing is going to be that we had to use the quadratic formula to find the x-intercepts. And sometimes that's going to happen. Most of the problems that you'll probably see in your homework will be structured in such a way that finding the x-intercepts may not require that. You may just have to be able to factor, but you should be comfortable with using the quadratic formula. And so if you need to, don't be afraid to do so. And in those cases, for the purposes of graphing, it's okay to approximate the values on your calculator. All right, this these were some examples of how we can reasonably quickly, sketch graphs of quadratic functions. And so you know here, the main thing, finding the vertex, knowing the concavity, the direction the parabola is going to go in, and then finding the intercepts. Once you have that, you can draw a pretty good graph for the quadratic function. All right, so that's all I have for you today regarding this topic. And once again, if you do have questions, you can contact me via email or by whatever means that you know to contact me in. All right, so have a good day, and I'll see you soon.